Good. All right, so which one was it again? 174? Okay. So guys, this is page 356. Whoa. $26. Right? One about car pollution? So they give you a sample of 7 cars. So somebody sent me an email about they never give me the standard deviation for one of these problems. It's because they give you the list of data. So you can put that into list 1. Once you put it into list 1, how do you get the calculator to spit out the mean and the standard deviation for you? 1 var stats. So you go back to your little calculator Bible, still on there, right? Like I promised in chapter 3, once you get out of chapter 3, I'm never going to make you make that table to find a standard deviation again, because we got too much other stuff to worry about. Give me the standard deviation, let me worry about the other stuff. Right? So the first thing I need you to help me out on, Huang, is did you get the sample mean and the standard deviation from this data?
I got the sample mean, but I didn't get the standard deviation because I forgot to put it in the calculator.
Ah, okay. That'll make this doable. So you got to figure out the x bar, the s, and that you put in lists. So you can put that in list 1 and do 1 var stats. Once you've got these guys, what do you have to use considering something I've put up here? What can you use to make the confidence interval? What do you have to use to make the confidence interval? Formula. I like that. That's interesting. Be a lot more specific. Which formula? I mean, tell me that at least. Do I use this one?
Is it the...
Or do I use this one?
Use the T.
Or do I use this one?
No.
I can, of course, kill that one because this is about making a confidence interval about a mean. One of those two, I know S, so it must be the one that's got S in it. I'm not sure how to make it easier than that, really. Now, the thing I don't like about this problem, I think it's one of those crazy problems. It never says in here anything about normality, does it? Those silly people. All right, so I guess it's saying forge ahead even though you don't have what you need desperately. So if this problem was just sitting somewhere by itself, you would look at it and say, I can't do it. Thank you very much. Right? It's got to be normal to use Z or T. So if my sample size is not big enough, what's my sample size here? 7. All right, cool. Right? And that's definitely not big enough. Big enough would have to be more than 30, yeah. Cool. But so we just forge ahead. We know we shouldn't be able to do it, but we just do it. Somebody somewhere knows it's normal or something, so we just do it. Is that enough to get you going? I mean, that's...
Yeah.
You want to get these from your calculator. You can use this formula here. What's the degrees of freedom going to be?
6.
Good. 1 less than the sample size. If you've missed a few classes, you have no idea what the hell that is. You should probably come see me. Okay, cool. So any other questions about? So a couple of them are like that, right? They give you a list of data. You've got to find your own mean and standard deviation. That's a giveaway that it's going to be a T interval, right? Because you're going to use your own standard deviation. All right.
Nice shirt.
Thank you so much. It's going to be hot as hell, so I thought, what T-shirt do I have that's clean at the moment? And that may be math related, so that was the one. Okay, so if there's no other questions, which always makes me a little worried, we're going to get back into chapter 8. So this is actually something we've known for a really long time. And let me try to take a big old step back first let's say that somebody says that 10% of M&Ms are green. So let's say we got that. And if I have like, if I get one of those big old bags and it's got 400 M&Ms in it, what's the average number of green M&Ms? What's the standard deviation in the number of green M&Ms? So this idea by itself is important. The number I get here is not going to be the number I'm going to have in every single bag. It's the number I would expect. That's why another name for this in this case is expected value. It could be more, it could be less. This number, of course, tells me how much more or less it should be on average, right? Cool. So I just want to make sure that we all understand the two numbers that we're using all the damn time. We have to understand what they mean to make sure we understand why it makes sense what we do with them. So somebody help me out. What's the most beautiful little formula for mu?
40 N and P.
N times P, I love it. So it'd be 400 times 0.1. So I'd expect about 40 green M&Ms out of a bag of 400. And what's the standard deviation? What's that formula?
Square root N P Q.
I love it. So square root of 400 times 0.1 times 0.9. Is that pretty cool? 0.9. That's just the rest, right? If P is 10%, Q must be 90%. That comes out really nice. I didn't mean to do this, but doesn't it just come out to be 6? Yes, cool. I wish I could say I did it on purpose, but I didn't. Just got lucky. So can somebody tell me right now, based on what we had done in the past, what's the max and min expected value of green M&Ms?
Plus or minus 10 times standard deviation.
Yeah, so it'd be the mean minus 2 standard deviations and the mean plus 2 standard deviations, right? And anything that falls outside of that range would be considered, which would be evidence that that bag, what? There's a lot of different ways to finish that sentence, but what?
It's unusual.
Okay, is unusual.
Isn't accurate.
If I was a conspiracy theorist and I thought that there was somebody after me, they didn't want me to have my green M&Ms that I loved. I want my green M&Ms. Every bag I buy, they know where I'm going. I don't know. I got Mel Gibson in my head now. If you ever saw that movie, Conspiracy. So let's finish it out. 40 minus 12.
28.
40 plus 12.
52.
So if I do this and I get a bag of 400 M&Ms and I'm OCD, I sit down, rearrange all of it, and I count, and I get like 5 green. That is damn unusual, right? Because the lowest I should expect is 28. That is evidence that that bag is unusual, but that might be evidence of something. Wherever they came from, they got their sorting method is wrong. Maybe some bags get crazy amounts of green, and mine was one of the ones that didn't get many green at all.
The amount of percentage could be wrong.
Yeah, this stated percentage from the exactly. It's evidence that this could be wrong. That's what I was waiting to hear. That's less conspiracy theory and more if they claim that 10% of the M&Ms are green, and I get 5, then that's evidence that it's less than 10%. Now, do you guys see how this is playing right into chapter 8? I got this mean here, this 40. I got this maximum expected value and this minimum expected value, the 28 and the 52. If I find a sample that is in here, for example, doesn't that show evidence that this is wrong? Because it's freaking unusual, given that this is right. So what's more likely is that this itself is wrong. Doesn't that hopefully feel like what we were talking about last time with the hypothesis test? I want to set up, now these here, in this case, are set up by this formula. And does somebody remember what the 2 was? Why did we use 2 standard deviations? What percentage that relates to outside? 5%. That would be like alpha of 0.05. Right? The area of the tail, 0.05. So it sounds exactly like one of our hypothesis tests that we just got into. Right? Believe it or not. So these benchmarks act a lot like our z-score benchmarks, but they're just more specific. Our z-scores give us a lot more information. Here I just roughly know that it's unlikely and that it shows evidence that this is wrong. If I do the hypothesis test, I get a lot more information. How unlikely is it? Where exactly do I fall? I can also change the benchmark, move it around. But I really want to show you guys we've done Chapter 8 before. We just didn't use all the steps. We didn't call everything by the name we call it in Chapter 8. But it's old news. Now, the other thing people hate about Chapter 8 is the fact that every problem seems to take about a century to do. Right? Well, there's 1 century. Let's do number 5. We'll go through 80. Oh, great. So I'm gonna do a couple with you, and then I've got kind of like the outline of what a problem, the steps you go through, and I'm gonna let you guys work in groups on a couple out of the book. But we're gonna do a couple together first. So looking at this problem is old news, right? This is old stuff. What was important to know here?
The number and the percentage.
Cool, right? The specifics. So I need to know sort of the claim. So obviously it's important to find the claim. I then have to know what's going to show me something. That's what these set up, right? And then I got to go actually take a bag and see where I take a sample and see where it falls. That's exactly the same steps. It's just a lot more detailed in the hypothesis test. So let's go through one. Let's go through one. And just to tell you right now, A2 I will come back to. A2 has got a lot of what I call side details. So I disagree a little bit with the ordering of the book. I wanted to get you the main thrust of how these problems work, because A2 is everything on the sides of this problem. A2's got like just setting up hypothesis statements, and then it's got just calculating test statistics, blah, blah, blah. Right? I think it makes more sense if you give me the whole damn problem to do. Don't just make me artificially stop somewhere. So let's do one out of section 8.4. Because I don't want to do the one with p-hats yet. Because that adds a little bit of freakiness in there. Let's do something that's vaguely interesting here. Well, all right. Let's do 14. Why not? 14 is interesting, at least in the sense that how do you take a sample of bears? I don't want to have that job of weighing a bunch of freaking bears, but somebody does. This is page, not gummy bears. I have the problem with diminishing sample size over time. Oh, shit. So section 8.4, page 419, number 14. Read through that real quick. It's a small one. That's kind of nice.
Can you put it up, your book?
Oh, yeah, sure. Oh, you don't do this. Oh. That one just makes noise currently.
Starting a fire and add it.
Oh, sure. Well, that's exciting every time. Okay, let's see. Oh, it's this one. Yes. So 14, holy crap. 14 weights of bears.
Thank you.
Blah, blah, blah. Okay. So the first place, the place you start is what is the claim? Because that's really what drives everything. It drives the fact that I'm doing anything in the first place. What's somebody's claim?
All such variables are greater than
Good. So we're trying to say that the population of these bears have a weight more than 150 pounds.
A mean weight.
Yeah. So which one is that going to be? The hoe or the high? And this is where if you weren't here last time, you're going, what the hell did I miss? High, because the hoe has got to have the equal sign. I love it. So this is going to be the hoe and the high, sorry. What's the hoe going to be?
less than or equal to 150.
Just the opposite. I love it. I think the book just puts an equal sign there, but really it should be the opposite. So who can tell me how many tail tests will this be? One tail, because I'm only interested in greater than. That's the only thing that's going to show me something. If it's less than, it's not going to be evidence of anything. So it's going to be a one tail test up here. Okay, cool. The really nice thing is, just like in algebra, where this told you which direction to shade, same thing. This tells you where the rejection region is going to be, where you shade the rejection region. I love it. Yeah.
One more time. Why was it one tail? Because you have a non-equal.
The only way to show evidence of greater than 150 is to be on that side. If I would have said, I don't think they weigh 150 on average, well, now what would be evidence? It could be lower or greater. Two-tail test, right? So the first piece is, what the hell are you talking about? Kind of important. The second piece is, what the hell are you allowed to use to talk about it? So in this case, can I use Z, T, or nothing?
Z. Z because you have a population standard deviation.
That's one thing. And
And it's greater than 30.
I love it. So you need two things. To do anything, to not be nothing, you've got to have a normal distribution. Do they tell me it's normal? No, but the n is, yeah, it's 54. So A, n is 54, greater than 30, check. B, sigma known, check, z-score. When do I have to use a t-score?
When you don't know this population.
Good. When you only know S, you don't know sigma, and it's still skeletal, got to be normal, though, right? Okay. How we doing? So it's got to be normal, period. T-scores were invented for when I don't know this. If I know it, I don't need T-scores. I can use Z-scores. Okay. Step 3 is going to be setting up the benchmarks. How far away will show me something, right? Well, that's what the hell is that? What tells me that? What tells me how far away I've got to make it? What part of the problem? I don't know if I've used this word yet. Have I used these words yet? The significance level?
5%.
So that's the same thing as alpha. That significance level is the same thing as alpha. It kind of makes sense. If I make it 0.05 and I get in there, that's significant. If I make it 0.01, that's even more significant. It's harder to get in there then, isn't it? It would be even further away if I made it only 0.01 instead of 0.05. So that's why it's called significance level. It tells me how significant my findings are. So I know alpha is 0.05. Let me title this. This is the critical or rejection region. Cool? So alpha is 0.05. How many tail tests? One tail test. We're allowed to use Z's. Cool. Just to show you guys again. What did I just say? Oh. So it's a one-tail test. Alpha's 0.05. I want to use the z-score. I know I'm looking at the cheat chart, but as long as I go all the freaking way down, 1.645, that's my critical z-score. That's my benchmark. It says, for this case, since we gave you 0.05 as your level of significance, you got to make a sample. You got to find a sample that falls more than 1.645 steps away, standard deviations away. That would be far enough away to say, whoa, that middle must be wrong. You found something crazy far away. That's the idea. Just like finding 5 green M&Ms in a bag when there's supposed to be at least 28. That's farther than far enough away, right? Same exact idea. So here, this will be, I'm on this side here, right? Can somebody say that in words for me? What does that mean in words? How am I going to use that in the next step, really? What does my sample, my Z star, have to do? If my Z star is greater than, we will reject the hoe, right? That's the whole idea. And again, I desperately want you guys to understand. If I find something, here's the 150 here, right? There's the 150. We're saying, okay, assuming that's really the real mean. If I get way the hell out here, that's probably not the real mean. That's evidence that somebody got it wrong. They probably didn't want to weigh the bears. The bears were biting and clawing. They're like, screw it, you look about 150 pounds. Right? You guys kind of see what I'm saying? Whatever happened, it must be wrong. Or maybe the bears are finding more food now. So overall, the population is getting healthier and they're weighing more, right? So it could be evidence of some kind of environmental change. Or if it's going down, maybe there's pollution or the animals are being driven out because of building houses and they have nothing else to eat. And more bears are showing people's backyards trying to go through their garbage cans, right? So they're getting less and less healthy. I mean, that's what this kind of test does. Okay. Yes, ma'am.
How do you know that the z-score is 1.645?
So alpha, the amount of area in the tail or tails, in this case tail because it's one tail, alpha was 0.05, right? They told me in the problem it's 0.05. So the area in this tail, this one tail, is 0.05. So if you look up in the T-chart, area in one tail, 0.05, right? One tail, 0.05. As long as you go all the way down, that's a z-score. 1.645. If I stop, that would be a t-score, corresponding to some degree of freedom, right? As long as you go all the way to the bottom, that is a z-score. That's why this stupid thing is beautiful for hypothesis tests. Hypothesis tests suck enough already. Thank God we have a one tail and a two tail. Break it up, great, right? You still have to know if it's a 1 or 2, but if you know it, you can look at that one or you can look at that one. It's awesome. Okay. I was just not thinking to myself, where's my book? Well, right there. Now that we set up how far away is far away enough, incredibly enough, I go and find out how far away we made it. Right? That only makes sense. Erase my M&Ms. I like the M&M problem, and I want you to keep in mind that they're the same thing because it's a lot more tangible. You say 20 M&Ms, you're like, well, I can imagine. I get 22, and I'm a little miffed. I get 5, and I am very curious. What the hell happened here? That's way far away, right? It's exactly what we're doing. We got to find, if we find something further than this, 1.7, 2.9, whatever, that's evidence that the middle here is wrong. It really shouldn't be there. It should be up further. So step 4, sample information. What do you know about the sample? see.
And 54.
There you go. Oh, and that's this side. That's definitely good. They put the bears to sleep. I kind of skipped over that word. That makes it easier. So sample of 54 bears has a mean weight of 182.9. Right? So X bar is, I just said it and I forgot. Thank you. What's S? I mean, not S, sigma. They tell me, see how they're very careful about it? Why do we know it's sigma? Because, well, they were really nice in this problem. They put the symbol sigma. But they could say, assuming that all bears have a standard deviation of all, that's the population, that would be sigma, right? So standard deviation is 121.8. Holy crap and a half, bro.
Is that possible?
Yes, it is, actually.
Oh, cuts to results.
Totally possible, right? So obviously, I want you to see how this is not a normal distribution. I don't care how many bears you pick. If you plot the individual bears, it's not going to be normal because a couple steps away, you got no negative weight bears. There's no black hole bears, right? So this is not going to be normal no matter what you do. But if you plot the sample means, as long as you have more than 30 of them, those will become normal. The standard deviation will become small enough that it won't go to 0 anymore, will it? That's the problem. I love the fact that you guys are kind of worried, and so was I when I first looked at it, but this is totally possible. You just have some really fat bears, and then some really skinny bears, and there you go. You got a huge ass standard deviation, right? That could happen. What's N?
54.
So what's the new standard deviation for groups of 54 bears?
Standard deviation.
I like it. Oh, do have 2 more calculators. Somebody's got to borrow one. Yeah, what do you get?
16.
I like it. Okay. So I want this to become an automatic. There are 4 things you need before you can get into a z-score. X bar, sigma, and then change sigma, right? So now you can do your z-score. Your z-score is the same as always. It's your data minus the middle. So there's my data, 182.9, minus the mean. What's the mean assumed to be? 150. So by hypothesis test, you can always go back here to figure out what you're subtracting. You want to see how far your data is from 150. You want to show that it's far away enough away from 150. So hours minus the 150 divided by the new dude here, 16.575.
1.985.
Do it again. 0.95? No, 1.95.
1.985.
85, okay. Either way, what happens? What do you do with that right now? And actually, I keep forgetting this, but that's my little Z star, right? I do that 2 reasons. We already have a Z score up here. I want to make sure that's different from it a little bit. And now I can find it visually. Where would 1.985 fall?
Way beyond.
Yeah, not back here. It's going to fall up here somewhere, right? Reject the hoe. Right there. Is everybody able to, if you can get up to that point right now and semi-understand what the hell just happened, I'm happy. Right? Now, obviously, at some point, you got to go beyond that because there's one more step here. Right now, just based on this, I can say reject the hoe. Which means what about the high? Support the high. If I can say that I've shown evidence he's wrong, that must mean I've shown evidence that he's right. Why can I never say absolutely somebody's wrong or right?
Because it's opposite.
Because where's our evidence coming from? A sample. And a sample could be wrong, obviously. We could just by chance happen to pick a lot of fat bears, right? But as long as we're randomly selecting them, there's a small chance that I'm wrong here. In this case, the chances that I'm wrong would be 5% chance. Okay. So just because our sample, just like if I took a bag of M&Ms and I saw 5 green, I'm like, somebody's out to get me. They know I like my green M&Ms, and they take it out of here somehow and they reseal it. Right? Over here, the same thing happened. We took a sample of bears. Their weights were further than what I would expect them to be, given this setup here, right? If they're further than this, that's unexpected, according to my alpha. Therefore, this can't be right. What's more likely is it should be higher. The population has a heavier average weight. So how do you write your conclusion then? Did we find or did we fail? Not find.
Not fine.
Did we fail or did we not fail? We succeeded.
No, we did not.
We found evidence, didn't we? Yeah, so we have found evidence. Now, what's my claim? Now, here's where you got to go back to your claim. And a lot of people make a big deal out of this. There's these charts and graphs and handouts and bullshit. Let's go back to here. What's your claim?
Just the average.
Which one?
High.
The high. So then you word it. Look what you already told yourself how to word this. Support the high. We have found sufficient evidence to support the claim. You just go back at the end. You say, which one was my claim? And then you word it accordingly. Right? If my claim would have been the hoe, I would have said we have found sufficient evidence to reject the claim that blah. And you can rewrite the damn claim from the problem. I don't care. As long as you're able to put this together and make sense, I love it. So we have found sufficient evidence to support the claim that what?
The black bear is more.
The population of bears have an average weight more than 150, right? Bam! Again, it's one of those problems that seems to take forever. And that's why people kind of give up on them and they get lost in the steps. All right, let me actually let you guys try one right now, and then we'll try to do one together, and we'll see how much time we have left. Let me give you this little outline of steps here.
Or maybe he's not.
Yeah.
Basically, it held like.
Let me pick a problem for us to try. Yeah, but okay. Number 8. Same section, right? Section 8-4. Page 418. Number 8. If any of you guys, are any of you guys possibly training to be nurses or something? Yeah. Okay. So have you guys talked about like blood analysis? Any of you guys work in a hospital, urgent care center or something? So when the doc does a, what's it called? RBC, CBC, complete blood count.
White count, thyroid.
When you get the results, aren't there ranges next to each one? So this is basically what that's talking about. It's built on the standard deviation, of course. What's acceptable range of values for like your white blood cells? What do your white blood cells do?
Hopefully they don't go too far up.
True. You don't want them too far up or down, but too far down is normally the big problem. That means your immune system can't fight things off. They're the things that fight off diseases and such. So there's a certain lower limit and upper limit that I expect to see. So that's what this problem is really kind of getting at, a little more detail. So try to do that problem using that outline. You don't have to use this paper if you don't want to. You just kind of keep it as reference if you want to, but you're not going to turn this in. We're going to do this together here in a minute. Yes, do problem number 8. Just like we did this problem here. Same steps. So just to make sure everybody's on the right track, to begin with, what is the claim being made?
The population
Mean
less than
lifespan 5.4.
So it won't always be this. So this is another one where that claim is going to go where? The low or the high? High, because it doesn't have an equal sign in it.
So the O will be
The opposite.
Or equal.
Beautiful. O's always got to have the equal sign in there somehow.
So O is greater than 5.
Greater or equal. So it's got to have equal sign. Possibly. Oh yeah, that's how you would word it here. Either support or fail to support. So it's definitely one tail because less than. So I'm only interested in that side. So if they said it's different from, that would be greater or less. That tells you where to look on the chart.
Okay, so your alpha, so your alpha is 1.1.
Do you need that still?
Yeah, I didn't write it. Copy off my neighbor. Sample view.
Whoa. Sorry. There wasn't much going on up here, so just recorded you guys for a while. All right, let me try to catch up to you. Huh. Oh, well, sorry. So the claim, like you guys told me earlier, was mean less than 5.4. So that's going to be definitely H1, which means the null is going to be the opposite, greater than or equal to. How we doing? Very interesting reaction from some of you guys. So one-tailed test, that inequality points me the direction of the tail. So ZT or nothing. Why? Why is it normal?
Because it's greater than 30.
Good. So n is 50 greater than 30.
And we know our standard.
The standard deviation of the population is known, right? A lot of people take that to mean if you know a standard deviation, you can use z-scores, but it has to be the population standard deviation to use z-scores. Now, what was alpha for this? 0.01. And it's a one-tail test, right? So if you looked it up, one-tail test, holy crap, did I freeze it? I didn't mean to freeze it. Oh, there we go. One-tail test, 0.01, all the way at the bottom, 2326, right? Sounds like that 233 number that we've seen before for things. So there's 2326. Now, one thing you got to be careful about, it's on that side, so it's got to be negative. We as the humans in this situation have to realize, okay, chart, you gave me the number, I know it's negative because it's on that freaking side. So be careful about that. If I find a Z star from a sample, if I find a sample that is less than this, that means it's further away from the mean than that can reject the hoe, support the high. Okay. Then you do the four things you need. You got the X bar, which they gave us, right? The 5.23, the sigma, and the N. You can make your new standard deviation, right? The one that's going to work for groups of 50. So I got 0.0764 rounding to, actually kind of rounded to 3 non-zero numbers, right? So my z-score was 223, negative. So what you guys got?
You wouldn't round that. You wouldn't round that.
So what?
You leave it at 30 digits.
Which one are we talking about?
Your new Z-score. your
That one there?
Z-
So, when I say 3 places, I mean 3 non-zero places. I think this has come up before. Because the standard deviation could be 0.00000000028. And if I round it to 3 places, that's 0. And all my data points might be 0.00000 whatever. So I gotta be careful. I really mean 3 non-zero places. Who rounded more? If you rounded more, what z-score did you get?
241.
All right, and see how much it changed? And if it would have been a rounding that would have made it go the other way, you might have actually done the opposite of what we should have done here. So what do we do? Negative 223, did it get far enough away?
Yep.
Did it? How far did it have to get?
Rejected.
2326,
That's good ones.
right? So did it get in here?
If you're off the screen.
Oh, I'm sorry. Did it get in here?
No. It's positive.
Here's 0, right? So where's negative 223? Isn't it on this side of 232? All right, it's a number line. That's all it is. So I didn't get further than 2326.
To reject
Right.
the high and support the low.
Careful. So here we got to be careful. You always reject or fail to reject the hope. This is really semantics on one level, but it's also all about what we can and can't prove. You either reject or fail to reject the hope. Support or fail to support the high. Yeah. Just because this sample didn't show evidence doesn't mean that some other sample might not. If I said support the hoe, then I would stop. But maybe I should keep going. We got damn close, didn't we? Maybe I should go out and take another sample, and maybe then I'll be 2-4. I'm not going to give up. So I remember when I first taught this, and basically I say the same thing still, is you're never going to say the hoe is right. You're going to say no. I'm hearing what I'm about to say. That hoe is wrong. We're always thinking that that hoe is wrong. We want to keep going. We're never going to accept it. We're never going to support it. We're going to reject it or fail to reject it. Well, I failed right now. You won the battle, but you haven't won the war, right? We're going to keep going. You guys understand that? So there's less options for wording this. That's nice. You reject or fail to reject. So in this case, we fail to reject the hoe. Am I back on the screen? Which means we fail to support the high. If I can't say the hoe is wrong, I can't say the hoe is right. The high is right. All right. Jeff. If I can't say this first guy is wrong, I can't say this second guy is right. How we doing? So when I fail across the board. When I don't fail, I succeed across the board. Right? So did we find, I gave away the answer right now, but how do we word the conclusion now? Yeah, we failed. We have not found sufficient evidence. In this case, what's the claim? The claim is the high again. So we failed to support the high, so we have not found sufficient evidence to support the claim that the samples from a population where the average red blood cell count is less than 5.4, blah, blah, blah. That's really just copying right out of the book, right? Just perfect. Just copy the claim back down. See a lot of concerned faces. But the biggest problem with these is normally semantics, really. The math of it's truly not difficult compared to the other stuff. It's the same stuff we've been doing for a while, really, the math of it. Okay. But I'm really not a firm believer of memorizing a lot of crap or having big charts and crap. I don't personally like that. I just want to say what makes sense here. Right? If the high is the claim, my wording is going to be support or fail to support the claim because I'm going to have to talk about the high for the claim. Okay, so let's do one more. Well, let's do one together. And real quick, section 8.4 is using z-scores. Section 8.3 is all about p-hat stuff. So what have I left out? T-scores. So section 8.5, T-scores. So it's really the same damn thing. You just look at a different chart to get this dude, right? We looked at this. You don't even look at a different chart. You just stop so you get a T-score, right? You got to look at degrees of freedom and get a T-score. Everything else is the same exact setup. So let's do a P problem. This is one from section 8.3. Yeah, P hat, P problem, yeah. Sounds like if you have a little kid, if you have a son or a daughter, sometimes we have a P problem. That's funny. Yes, ma'am.
When we look up the z-score for the last problem, it was a 2.326. How do we know it's negative?
How do you know it's what?
Negative?
Just because it was on that side. Wasn't the tail on that side?
That's true.
And aren't negative z-scores on that side? The chart's not going to give me negatives and positives. It shouldn't have to. It just gives me the number. I've got to realize, oh, it's negative because it's on that side. Yeah. Otherwise, the chart be twice as big as it really needs to be. Okay, so let's do on page 409. Oh, let me see. It don't matter. Number. Oh. I don't care. Number 9 is fine. One thing I really don't like about Triola is very often his examples are not as interesting as they could be. So I'm sure you guys probably agree.
What income? Or voting?
Number 9, income.
What page are you on?
409.
409.
Figure too high.
Oops. Okay. Real quick, before you guys get into that problem too far, a real quick word about this, and I'm waiting, obviously everybody's waiting for more details, but did you hear a little bit about when they got word about where Osama was? It was based on unexpected behaviors, right? I don't know if you guys heard about this.
Yeah.
They noticed that there was certain numbers of people going to this place. It was a slightly richer looking place. There was no internet access, no
Yeah.
phone.
8 times the size of the.
Once you get to a certain critical mass of unexpected things, they say, we got to check these things out on the list that fall into this region of unexpectedness. That's exactly the freaking thing we're doing now. It's not, they don't do it nearly as technically as we do, right? Because if you're too technical, you're going to miss some good leads. But it's still the same idea, right? It's a collection of things. You get to a point where, like, that's really unexpected. Let's go check that out. This is what they did. That's how they found it. So yes, statistics saves lives. No, I'm sorry.
Well, this really doesn't save lives.
Eventually it does. It's all about applying it correctly.
With the blood cell counts. No,
Oh, what about them?
well, without that data.
Without knowing that, we wouldn't know who to identify as a possible worry spot. Yeah. This guy's probably.